Good morning all. Today we are going to handle the topic equivalent circuit of transformer and their numerical problems. This is a very important topic. In this diagram, both the primary and secondary windings of the transformer are shown with both their resistance and leakage reactance were taken out from their windings. If you see in this figure, this R1 and X1 is indicating the resistance and leakage reactance at the primary winding. Similarly, this R2 and X2 is indicating the resistance and leakage reactance of the secondary winding. This R1 and X1 together comprises of the primary impedance, and this R2 and X2 together comprises of the secondary windings impedance, which is represented as Z2. We have seen in our last video session, this resistance R2 at the secondary side can be shifted to primary side by dividing it with K square. Similarly, this resistance R1 at the primary side can be shifted to secondary side by multiplying it with K square. In the same manner, the leakage reactance X2 can be also shifted to primary side, and the leakage reactance X1 also can be shifted to the secondary side. In this diagram, both the resistance and leakage reactance of the secondary winding has been shifted to the primary side. When it is getting shifted to the primary side, it will be represented as R2 dash and X2 dash. So this primary side will be having the total resistance of R1 plus R2 dash and total leakage reactance of X1 plus X2 dash. This R1 plus R2 dash is indicated as R01 and X1 plus X2 dash is represented as X01. The relation between R2 dash and R2 is R2 dash is equal to R2 by K square. Similarly, the relation between X2 dash and X2 is X2 dash is equal to X2 by K square. It is also possible to shift the resistance and reactance at primary side to the secondary side. When we do that, this R1 at the secondary side will be representing as R1 dash, and X1 at the secondary side will be indicating it as X1 dash. R1 dash will be related with R1 as R1 dash is equal to K square R1. Similarly, X1 dash will be related with X1 as X1 dash is equal to K square X1. That is, you must keep in mind that while shifting any primary resistance or leakage reactance to the secondary side, you have to multiply it with K square. And when shifting the secondary resistance or secondary leakage reactance to the primary side, you have to divide it with K square. The diagram of transformer and their corresponding equivalent circuit is shown here. This much portion of the equivalent circuit will be representing the ideal transformer, that is without resistance and leakage reactance. We have studied the concept of ideal transformer in our previous video sessions. R1 is representing the primary windings resistance and X1 is representing the primary windings leakage reactance. Similarly, R2 and X2 are representing the components at the secondary side. We are giving V1 supply at the primary side, and we are connected a load ZL at the secondary side. Secondary terminal voltage is represented by V2. The primary winding induced EMF is E1 and the secondary windings induced EMF is E2. In our last video session, we have seen the equivalent circuit of transformer under no load condition. From there, we very well know that what does this I0 indicates, IW indicates, and this is actually I nu. That is the magnetizing component of the current, and this is working component of current, and this I0 is indicating the no load current. In order to simplify it further, either we have to transform the components which is present at the secondary side into the primary side. Then the equivalent circuit which will be obtained is said to be the primary equivalent one, or else we can transfer the primary side components into secondary one. Then the simplified equivalent circuit obtained will be said to be the secondary equivalent one. First, let's see the primary equivalent circuit of the transformer. For that, we have to transfer all those components which were present at the secondary side into the primary one. The secondary circuit which we have seen in the last slide alone is shown here, and its equivalent primary values are shown in this circuit. That is, when we are transferring this R2 to primary one, it becomes R2 dash. It can be obtained by dividing R2 with K square. Similarly, when we are transferring this X2 to primary side, it becomes X2 dash. It can be obtained by dividing X2 with K square. While shifting the secondary circuit to the primary one, the value of E2 dash, that is, when we are shifting this secondary to primary, it becomes E2 dash, and the value of I2 becomes I2 dash. The value of E2 dash must be same as that of E1. Similarly, the value of I2 dash must be same as that of I1. Since E2 dash is same as that of E1, we can easily write E2 dash is equal to E2 by K, because E2 by E1 is equal to K. So from there I can write E1 is equal to E2 by K. So easily I can say that E2 dash is equal to E1 is equal to E2 by K. So that's how E2 dash will be related with E2, that is E2 dash is equal to E2 by K. Similarly, by using the relation of transformation ratio, we can say that I2 dash is equal to K times I2. This is possible because when we are transferring the secondary side to the primary side, the value of I2 dash must be same as that of I1. And you know that I1 by I2 is equal to K. From there you can easily say that I1 is equal to K times I2. So I can write I2 dash is equal to K into I2. So it's very clear that when we are transferring the secondary side to the primary side, the voltage components, that is E2 or V2, it becomes E2 dash and V2 dash when we are transferring to primary side. This transfer can be done by dividing it with the term K. Similarly, the current at the secondary side can be transferred to primary side. When it is getting transferred to the primary side, it becomes I2 dash. And the relation between I2 dash and I2 can be achieved by multiplying I2 with K. The resistance and reactance term can be transferred to the primary side by dividing it with the term K square. So now the circuit is indicating the primary equivalent of the secondary circuit. After joining it with the primary side, the complete equivalent circuit becomes like this. This portion is indicating the primary side and this portion is indicating the primary equivalent of the secondary side. As the value of this no load current I0 is very small, this branch can be shifted to this point. Then the equivalent circuit becomes like this. See, we have shifted that particular branch to this point. Now if you see in this diagram, this R1 and R2 dash are in series and X1 and X2 dash are also in series. So this R1 and R2 dash can be said to be the primary equivalent resistance. It is usually represented as R01. Here it is indicated as R equivalent, but usually it is represented as R01. Similarly, X1 plus X2 dash can be indicated as X01, and these two together can be said to be the primary equivalent impedance, which is usually indicated as Z01. As I told you, the value of I0 is very small. We can simply neglect this branch also. Then the equivalent circuit can be drawn like this. This is actually the final equivalent circuit of the transformer. In this problem, the rating of transformer, voltage rating of transformer is given. This is actually the transformer under no load condition. So it is taking a no load primary current of 0.6 ampere. The value of I0 is given and it absorbs 400 watts. You are asked to find the magnetizing and iron loss components of the current. That is, you are asked to find the I nu and IW value. This IW and I nu's value is asked to find. And in the problem, it's under no load condition. That means there is no load connected at the secondary side. So definitely this value of current will be 0. And the current which will be taken from the primary side will be only the I0, because there will not be any flow of current through this path as it is open circuited. So if you see here, the voltage which will be appearing across these two branches will be V1. You will be able to understand more clearly from this diagram. See, the voltage which will be appearing across these two branches will be V1. And the value of V1 into IW is given as 400 watts in the problem. See, the transformer absorbs 400 watts. This 400 watts is actually the iron loss. So 400 watts, 2200 volts. This is 400 watts and this is 2200 volt. This data are given. So from here you will be easily able to find the value of IW. You have to divide this 400 with 2200 volt. As I told before, V1 into IW will be giving you the value of iron loss, that is actually 400 watts. So from there you can easily find the value of IW, that is the iron loss component. We will also call it as active component or working component. Okay, once after determining the value of IW, you are quite familiar with this vector diagram. This is actually the vector diagram of transformer under no load condition. So now you know the value of IW, and the value of I0 is given in the problem as 0.6 ampere. From there you can easily find the value of I nu. I nu is this particular component. Please note the correction, this is actually I nu, which is actually the magnetizing component of the current. You can easily find it by square root of I0 square minus IW square. Here also one correction is there. This is not actually the whole square. This is just 0.182 square. Then you will be getting the value of I nu. In the second part of the same problem, you are given a 2200/250 volt transformer, and the no load current is 0.5 ampere at a power factor of 0.3 on open circuit. That is, this value is 0.5 ampere and this angle is cos inverse of 0.3. You are asked to find the value of IW and I nu. IW can be easily found out by I0 cos this angle, and I nu can be easily found out by I0 sine of this angle. That is also shown here. This is actually a problem which is associated with transformer under no load condition, not the problem which is linked with the equivalent circuit of the transformer. This is a problem associated with the equivalent circuit. The power rating of the transformer is given as 30 kVA. Voltage rating is 2400/120 volt. Has a high voltage winding resistance. High voltage means here it is primary side. There is the value of R1 is given and X1 is given. R2 and X2 values are also given. You are asked to find the equivalent winding resistance, reactance and impedance referred to high voltage side, which is actually the primary side, and the low voltage side, which is the secondary side. So in the first part you are asked to find the equivalent winding resistance, reactance and impedance referred to primary side. That is, you have to find the value of R01, X01 and Z01. As you know, R01 is actually the sum of R1 and R2 dash. We have seen that here. R01 is actually the sum of R1 and R2 dash. X01 is actually the sum of X1 and X2 dash. Once after finding the value of R01 and X01, you can easily determine the value of Z01. The values of R1, R2, X1, X2 are given in the problem, and even both the primary side and secondary side voltage ratings are also given, so you can easily find the value of K also. Once if you know the value of K, you can easily determine the value of R2 dash and X2 dash from there. R2 dash is actually R2 by K square and X2 dash is actually X2 by K square. So R1 plus R2 dash will be giving you the value of R01, X1 plus X2 dash will be giving you the value of X01. You must draw this diagram also along with such sort of problems. This diagram carries some marks. So if you see here, you can find the value of R2 dash by R2 by K square. So R01 can be determined by R1 plus R2 by K square. K is found out to be 1 by 20. So after solving this, you will be able to get the value of R01. Similarly, you can find the value of X01 also. From both these values, you can find the value of impedance as square root of R square plus X square. That standard relation can be used to get the value of impedance. Next, you are asked to find the equivalent winding resistance, reactance and impedance referred to low voltage side. That is, you have to find the value of R02, X02 and Z02. So you have to transfer the primary resistance to secondary. So when the primary resistance is transferred to secondary, it becomes R1 dash, and when the primary leakage reactance is transferred to secondary, it becomes X1 dash. The value of R2, X2 is given. R1, X1 is also given. As you know very clearly that R1 dash can be easily obtained from R1 by multiplying it with K square. Similarly, X1 dash can be determined from X1 by multiplying it with K square. So you can find the value of R02 and X02 then. Next, you can easily find the value of Z02 from the values of R02 and X02. That is also shown here very clearly. Please don't forget to draw those diagrams for this problem because that diagram also carries certain marks. Now let's see the third problem. The power rating is given as 50 kVA. Transformer voltage rating is 4400/220 volt. R1 value, R2 value, X1, X2 values are given. You are asked to find the value of R01. Just like in the previous problem, you can easily find out that. Then you are asked to find the value of R02. Similarly, you have to find the value of X01 and X02. Then Z01 and Z02. So from here till here, you can follow the same steps in the previous problem to find the answer. Now, here you are also asked to find the total copper loss, first using individual resistances of the two windings and secondly using equivalent resistance. Individual resistances means you have to find the total copper loss by using R1 and R2. If you see in this diagram, the copper loss which is occurring here is I1 square R1 and the copper loss which is occurring here is I2 square R2. So the total copper loss will be I1 square R1 plus I2 square R2. So you can either find the total copper loss by adding I1 square R1 and I2 square R2, or else you can find the value of copper loss from this equivalent diagram. This is actually the primary equivalent. If you are neglecting this I0 current, there is this branch hole if you are neglecting, then the current which will be flowing through this will be I1, and this I told you before, this is actually R01. So the loss which is occurring in this equivalent branch will be I1 square R01. Similarly, we can obtain the secondary equivalent circuit. In that particular circuit, this resistance becomes R02, this becomes X02, and the whole impedance of the secondary equivalent will be Z02. This voltage will be V1 dash and this voltage will be V2, and the current which will be flowing through this branch will be I2, not I2 dash. Just like we have obtained the primary equivalent circuit, you have to obtain the secondary equivalent circuit by yourself, following the same steps mentioned to achieve the primary equivalent circuit. X01. The copper loss which you will be obtaining from the primary equivalent circuit will be I1 square R01, and the copper loss which you will be obtaining from the secondary equivalent circuit will be I2 square R02, and the copper loss which you will be obtaining from this circuit is I1 square R1 plus I2 square R2. All these copper loss values will be one and the same. Let's see in this problem. First we are calculating the value of copper loss using individual resistances, that is I1 square. This will be R1, not R2, okay? Please note this correction also. I1 square R1 plus I2 square R2, you will be getting the value as 910 watts. Next, from the primary equivalent, you can calculate the copper losses I1 square R01, 910 watts. From the secondary equivalent also, you can get the copper loss value as 910 watts. This can be considered as a check to verify the equivalent circuit which we have obtained is the correct one also. You must draw the equivalent circuit both with respect to primary side as well as with respect to secondary side before solving this problem, because those equivalent circuit also carry certain marks. Hope the concept of equivalent circuit and the numerical problems associated with it are clear for you. Thank you.